Hello, class. Okay, so today we're going to talk about relative motion. So, like imagine that you were out, like in space or something, just floating around. And there's nothing nearby. Can you tell if you are moving or not? And that's actually not a simple question at all. This goes back to at least the 1600s. I know Descartes talked about this, and Galileo did as well. Newton definitely kind of built this into his mechanics. But it's definitely not a simple question. Like, can you tell if you're moving, or how can you tell if you're moving it or not? And seems to be the answer is that there's no such thing as absolute motion. Like, if there's a reference point, like say you're out floating in space, and then you see something, and you're getting closer to it, you might think, well, definitely now I'm moving, because I'm moving closer to this object. But what if you're not moving and the object is moving towards you? Is there any way to distinguish those two things? And the idea of relativity is that no, there's no way to tell. And so this idea of absolute motion does not seem to exist in our universe. So another way of saying that is all motion is relative. It's only meaningful to say that you're moving relative to something else. Like if you're floating around in your spaceship and you see yourself getting closer to an object, you can say you're moving towards it, it's moving towards you. You're moving. The two objects are moving relative to each other, and that's all you can really say. It doesn't even make sense to ask which is moving and which is not. However, I say that's like the principle, or just like this idea behind the relativity. But it's not a trivial thing at all. You could ask a similar question, like, what if you're accelerating? Can you tell if you're accelerating or not? And the answer to that question is yes. Kind of acceleration is something absolute. You don't need a reference frame. You don't need like nearby objects to determine if you're moving away from them any faster. Acceleration is something that is absolute. But like the philosophers in the 1600s, like Descartes and Galileo, I don't know if they were even called scientists back then, but yeah, they came up with this idea that motion is relative. And but that idea was actually abandoned in the late 1800s. And the reason why is we started to get an idea of what light actually is in the late 1800s. It's something you'll study in 122. But in 122 you study electric fields and magnetic fields, and there's a guy named Maxwell, which you'll learn about in 122, who came up with this idea of an oscillating electromagnetic field, where you've got these electric and magnetic fields that are oscillating and turning into each other, and this would create a wave that travels at a particular speed. And he had no idea what this wave actually was, but when he calculated the speed, he found that it was the speed of light. And so that raises some questions like, what is it moving relative to? And so when they came up with this idea that light is an electromagnetic wave, they actually kind of abandoned relativity, the principle of relativity, and said that doesn't really apply to electromagnetic waves. It applies to mechanics because relativity is built into Newtonian mechanics. But they said it just does not apply to electromagnetism. It's not a universal property of our universe. That didn't last too long, though, because in 1905, someone wrote a paper called On the Electrodynamics of Moving Bodies. And the person who wrote that paper was Einstein. No one knew who he was at the time. He was working as a patent clerk. But that paper was what we now call the theory of relativity. And at the very fundamental idea behind it is that what he called the principle of relativity which applies to the universe overall. So it applies to mechanics as well as electromagnetism. And as far as we know, there are just no exceptions to this. So as far as we can say now, all motion is relative. Okay, so we usually kind of ignore this fact. Just because, well, let me give you an example. Let's say we have a car. Let's call it car A. And I say it's traveling at 30 meters per second. Now, if I say the velocity of car A is 30 meters per second, you're probably not going to be very confused and say, 30 meters per second relative to what? Relative to a satellite that's orbiting the Earth? No, it's obviously relative to the ground. And so all velocities they can only be stated in a particular reference frame. But most of the time that frame is obvious. Like here, this is 30 meters per second relative to the ground, and that's so obvious we usually don't mention it unless we really need to. But there's a way we can do, like a shorthand way we can do this. I'm going to say the velocity of A relative to the ground is 30 meters per second. Okay, so when describing velocities, if we need to specify the reference frame, we have two subscripts. One is that the first subscript is the object, and the second is the reference frame. So if there's someone standing on the ground, this is a ground observer, they would see you moving 30 meters per second away from them. How do you know, how could this person know they're moving 30 meters per second? They could get out their stopwatch and time the car and say, okay, I mark where it is now. 1 second later, it's over here. That's a distance of 30 meters. So 30 meters per second. But now, let's say we have car B also on the same road, going in the same direction. And let's say car B is going 20 meters per second. So again, that'd be the velocity of B relative to the ground, 20 meters per second. Okay. Now, what if I ask this question? What is, I'm just going to write it down without saying it. What is VAB? So there's kind of two questions kind of disguised as one. On one hand, there's a numerical answer to this question, but another one, it's like, what does this even mean, VAB? Well, this would be the velocity of A relative to B. So B is the reference frame, so imagine you're in car B, you're going 20 meters per second relative to the ground, car A is going 30 meters per second relative to the ground, so what is the velocity of car A relative to you? And remember how this ground observer determined that car A was going 30 meters per second. They just, timed it. They said it was at this location at time t1, and then this location at time t2, and then just take the difference over time. So let's say someone in reference frame B does that as well. Let's say right now there's a certain distance between them, and between cars A and B. And that, say that, let's just say this is x equals 0. Then 1 second later, car B is going to be 20 meters away from x. To make it easy, let's say that both A and B started, side by side at t equals 0. So then, so here, I'll put it over here. So they were side by side at t equals 0, at x equals 0, and then 1 second later, car B is 20 meters away from this point, and car A is 30 meters away, and so the distance between them increased by 10 meters in a time of 1 second. So we'd say the velocity of A relative to B is 10 meters per second. And again, you could probably have figured that out on your own if I didn't explain how to do that, because this is not that complicated. If you just think about what it means, I mean, just you subtract them. 30 minus 20, you get 10. You do have to know like the subscript, but that's just conventions. You just need to know how to read this. Now we could ask another question. What about the velocity of B relative to A? So again, they're going to be separated by that 10 meters. But if you're in car A and you take, like you're going faster than car B, so imagine they're side by side, like you're side by side with another car, but you go forward and they seem to move back in that, from your perspective, they're now behind you. So they seem to be moving in the opposite direction that you are, and so VBA is minus 10 meters per second. So they travel the same distance. So it's like, two cars side by side. From B's perspective, A pulled ahead. From A's perspective, B fell behind. So, that's why they have that sign difference between them. And this is actually an example of a very important rule, which I'm going to write down. In general, we can say VAB equals minus VBA. So, like if you have VAB as 10 meters per second, if you flip these subscripts, you keep the number the same, but you put in a minus sign. And that's a general rule, so we'll write it over there. There's going to be two rules that we're going to come up with, and that's one of them. So I want to come up with a second rule next. Let's erase this. And what I'm going to do is... I was kind of mentioning something earlier, like you could figure this out on your own without having to have it explained to you, so why are we talking about this at all? Well, let's look at another example of a relative motion problem. Say you're in a car. That's what cars look like. Let's call this velocity of the car relative to the ground. And let's say that there's a raindrop, it's raining, and say there's a raindrop falling straight down. So the velocity of the rain relative to the ground is straight down. So the car is moving to the right, the rain is moving down. What is the velocity of the raindrop relative to the car? Now that is a much more difficult question, and if you've never done this before, you might not know how to figure this out. And so we're going to come up with a general procedure for dealing with problems in relative motion. So let's start with kind of the foundation of it. We're going to look at two general reference frames. I'm going to call them A and A prime. So let's say this is reference frame A, and this is reference frame A prime. So that's X and Y. This is X prime, Y prime. And we're going to say that A prime is moving at a certain speed, like in the X direction. These two share a common X direction. And so let's say this reference frame is moving in that X direction at a certain speed. So this would be the velocity of A prime relative to reference frame A. And let's say that there's a point P. So this could be like an object. Maybe there's a bird flying or something. Both people are looking at it. And what I want to do is I want to describe the position vectors for both observers. And we use the same subscript notation for position vectors as well. So this would be R PA. So this is, the object is P, the reference frame is A. And this is R P A prime. And we have another vector pointing, this vector here would be R A prime A. Okay. So remember, the first subscript refers to the object. So we're looking at like from the, from A to A prime. So the object is A prime, the reference frame is A. Similarly, this is PA, this is PA prime. Okay, so we just drew these vector diagrams. And again, this is another example of why it's so important to be able to look at a diagram and write down an equation. So let's think of tip to tail addition. And I'm going to write R A prime A plus R P A prime equals R P A. Okay, so yeah, I'm kind of regretting my choice of names right now. Yeah, it's fine as it is right now, but I can see a bit of a problem. I'm sorry, I actually want to change the name of this reference frame. I think it'll be a little easier to see because what we're going to do, so first off, we have this equation. And remember, everything is moving. So this is just like a picture at one moment in time. It looks like this. So if we take a picture at a later moment in time, everything is going to move relative to everything else. Like we know this reference frame is going to move over here. Maybe this point is moving as well. But we can redraw a picture. The same relation will exist at a later time delta t. Like the vectors will be pointing in different directions, but the same relation will exist. And so we often use prime for like a later time. So sorry about this. I think I'm just going to change this. Let's call this reference frame B. So we have A and B, and then we can use prime for something else. So I have to change a few things here. So yeah, we're looking at this vector is pointing to the object B from the reference frame of A. This vector is pointing to point P from the reference frame of B. And this one we leave alone. And so now this equation, we can say RBA plus RPB equals RPA. Okay, so basically I just had to change that name. So again, this is at t equals 0. Now just imagine everything moved a little bit. All right, let's just say, we can just say A, we'll leave A alone. Let's say point B moved over here and maybe point P moved over here. But again, we can just redraw these vector diagrams. They'll point in different directions, but they will have the same relation between them. So sometime delta t later, let's say our new diagrams, we'll just put primes next to everything. So this would be RBA prime. That would be this vector, that's RBA is what points from A to B. So basically if point B moved to the right, if this is RBA, this would be RBA prime. Or maybe I should say R prime BA, because the prime is the vector, not the reference frame. Okay. So yeah, like this picture, point B moved over a little bit because this reference frame is moving in the x direction. And so, yeah, that's what that vector would look like. And similarly, maybe point P moved, so these vectors would move as well. But the relation between them is going to be the same. So we have R prime PB equals R prime PA. And now what we want to do, kind of out of room, so I want to take this second equation and subtract the first equation. So, yeah, let's label these. Let's call this 1 and this one 2. So equation 2 minus equation 1. Okay, so we've got R prime BA minus RBA. Now, maybe this is where a point where I should pause for a moment and tell you we're going to do problems involving relative motion. But you are not going to be doing this. I mean, you can if you want to, but you don't need to be doing this. So what we're trying to do is derive a result, and then we can use that result whenever we need to. So again, if this is looking very complicated and not something you want to do, like on a homework problem or a test, you're not going to need to. It's important to do it once so we can see where this comes from, but then, yeah, the result is actually going to be very nice. Okay, so we take this term minus this term, and then this one minus this one. I'm going to put parentheses here. So then we have R prime PB minus RPB. And that's all I can fit here. But then I'll just do it on the next line. This would be R prime PA minus RPA. Okay, so we did that. And let's just look at this first term here. R prime BA minus RBA. So this is actually an accurate drawing because, you know, the displacement was purely in the x direction. Let's call this delta R. And this is delta RBA. So if we look at the displacement of point B relative to point A. So again, if we're picturing point A to be, you know, fixed, and B is moving in this direction, yeah, we get the right, you know, delta RBA. That would just be the displacement of that point relative to reference frame A. And similarly, we could do the same thing with the others. So what we have is delta RBA plus delta RPB equals delta RPA. Let me just double check these subscripts. BA, PB, and PA. And again, these are displacement vectors over a certain time interval. And we're kind of getting to the point now where if we just divide everything by delta t, this would be the velocity of B relative to A, just the displacement over time. And this is the velocity of P relative to B. That's the velocity of P relative to A. So let's write down that equation. And I'm going to do one more thing down here. I'm going to move things around. Let's write the VPA on the left side. And then on the right side, we're just adding these two vectors. I'm going to put this one first. So this is kind of our result here. Okay, so took a lot of work to get there. You know, we had to draw a picture and you know, do quite a bit of work. But the end result is actually very easy to not just use, but also to remember. There's this kind of subscript rule. So let's just look at the order of the subscripts. On the left side, we have PA. And on the right side, we have P, B, BA. So I'm just looking at the order of the subscripts. And this is a very nice way to organize things. You notice that these two terms in the middle are the same. They're both B. So we start with P, end with A. And just, you know, two in the middle are the same. So this is like the other rule. We have one rule here, and now we have this rule as well, or this rule, about how we can relate velocities in different reference frames. So I'm going to erase the picture. Actually, I'm going to erase everything almost, except for that top equation. I'm just going to change the notation a little bit, because the subscripts themselves don't matter. But we can say VAB. Oh yeah, these are vectors. We can say that's V. We can break this up into two pieces. And again, you can call this letter in the middle anything you want. So I want to just stick with AB for our main reference frames. Then we can introduce a new frame, and just like if you have VAB, you can write it as a sum of two pieces where you start with A, end with B, and the two in the middle are the same. And so this is what we need to know to solve these relative motion problems. And so I want to start out with a simple problem, which we've already done. But now we're going to use our rules to do this. So I think we had the velocity of A relative to the ground was 20 meters per second. And velocity of B relative to the ground was 30 meters per second. So let's draw this picture. Okay. And what we wanted to know, let's say let's start with velocity of B relative to A. Now again, intuitively, this one is going faster by 10 meters per second. So its velocity relative to A should be positive, and we should just say this is 10 meters per second. We can kind of just intuitively see that VBA is 10 meters per second. Well, I want to solve it using the rules that we have here. So we want VBA. And notice I didn't really write any vector notation because this is a one-dimensional problem. So vectors carry information about direction as well as magnitude, but if you're in one dimension, the direction is taken care of with a plus or minus sign, so we don't need to worry about that. So here we have VBA, and we can just write this VBG plus VGA. So let's check. We have BA, we start with B, end with A, the two in the middle are G. So far that's good. And then, well, we know VBG is 30 meters per second, but we don't exactly have VGA. We have VAG. So we can use this other rule and just flip the subscripts around. So this would be VBG minus VAG. Or 30 meters per second minus 20 meters per second is 10 meters per second. And so we got the result we were expecting. Except now this is kind of a systematic way to do this. You want VBA, just write it as a sum of two pieces that have a common, additional reference frame. And yeah, it wasn't that hard to do. So that's the idea here. Now, this is kind of the foundation. So I think that'll be a good point to stop this video because we derived our two rules. And we checked it to see if it makes sense with a problem that we already knew the answer to. But I want to do two problems to just as, or maybe I'll just do one and then one in class. I think that'll be good. So, but I want to do at least like one problem in 2 dimensions where it's not so simple. And then in class, I'll do an additional one. But I want to do that in a separate video so it's easier to find later. Okay, so I will stop this one here and then record another one with a problem.